I hope you are following the lecture sincerely and you are reading whatever has been done in the lecture, and then you are going back to the daily practice problem sheet and you are solving some of the questions. So in the previous lecture, we were doing a very important concept of Raoult's law. Okay. So basically in the last lecture, we discussed about the idea of Raoult's law and how Raoult's law can be used to get the pressure over the solution. Okay. So let's start the lecture. So we'll basically focus on the Raoult's law and the composition of vapor in this lecture. Okay. So in the yesterday's class, we were saying that suppose we are having a binary solution in which both the components are volatile. Okay. So this is basically having, as you can see, this is having two components, one which is A and the other which is B. Okay. Now because both the components are volatile over here, so both of them will form vapor. Okay. So we are saying that the total pressure over the solution would be the sum of the partial pressure of individual vapors. Okay. So this is basically the total pressure exerted over the solution would be the sum of the partial pressure of the vapor pressure of A and B. So now according to Raoult's law, we know that the partial vapor pressure, okay, vapor pressure exerted over a solution by a liquid will be directly proportional to the mole fraction of that component in the liquid phase. So PA was basically equal to P naught A XA and PB was P naught B into XB. And also we knew that XA plus XB is also equal to 1. Okay. So this was the concept that we did in the previous lecture. So today we are going to build more fundamental concepts on this and we are going to analyze this completely in terms of composition of vapor and how the distillation of such liquids are carried out. Okay. So let us see a very important aspect of the vapors now. So in this case we want to find out the composition of vapors. Okay. So we define the composition of vapor in terms of the mole fraction. So Ya is basically the mole fraction of A in vapor phase. Okay. So Ya is the mole fraction of A in vapor phase, Yb is the mole fraction of B in vapor phase. Okay, hope this is clear. So Ya is the mole fraction of A in vapor phase, Yb is the mole fraction of B in vapor phase. Now we know that the sum of their mole fraction will always be equal to 1. Okay. Now we also defined that the total pressure over the solution, total vapor pressure over the solution was equal to the sum of their partial pressures of the individual vapor component. So that would be P naught A XA plus P naught B XB. Okay. Now you have to just take care of one thing over here that is little confusing. XA is the mole fraction of A in liquid phase. Okay. Similarly, XB is the mole fraction of B in liquid phase. Okay. So this is a very confusing thing. Many of the students just get confused while solving the question and they put the value of XA and XB wrong and they take it as Ya or Yb. Okay. So you have to just keep this in mind because Raoult's law said that the vapor pressure over the solution due to a component will always be proportional to the mole fraction of that component in the liquid phase. Okay. So XA and XB are the mole fraction of A and B in liquid phase. We have assumed the mole fraction of A and B in the vapor phase to be Ya and Yb. Okay. Now from Dalton's law of partial pressure, we also know that the total pressure, okay, Dalton's law says that the total pressure multiplied by the mole fraction gives us the partial pressure of that component, right. So this is basic Dalton's law of partial pressure. Okay. Dalton's law says that if there are say mixture of gases, then the pressure exerted by the mixture of the gases will be equal to the sum of their partial pressure. Now, Dalton's law of partial pressure was true for all those gases which do not react chemically. Okay? So, we can say that according to Dalton's law of partial pressure, that partial pressure is total pressure into mole fraction. Okay? So, if we apply Dalton's law of partial pressure over here, so we will say that we know the total pressure exerted by the vapor. Okay? We also know the pressure exerted by the individual vapors. Okay? Pressure exerted by the A would be P naught A XA, pressure exerted by B would be P naught B XP. Okay? So, we will say that YA in this case would be equal to the partial vapor pressure of A upon total pressure. Total vapor pressure. Okay? So, this is, we will say that the mole fraction is equal to the partial pressure upon the total pressure. Okay? So, we can write YA as P naught A XA, which is the partial pressure of A, okay, divided by total pressure. Okay, total pressure is P naught A XA plus P naught B XB. Okay, so which we can write as PA upon P total. Okay, similarly we can write for the same expression for YB. So, YB will be the partial pressure exerted by B upon the total pressure. So, the partial pressure exerted by B we know is P naught B into XB upon P naught A XA plus P naught B XB. Okay. So, P naught A is the wave pressure of pure A, P naught B is the wave pressure of pure B. So, we can write this as PB upon P total. Okay. So, this is in accordance to the Dalton's law of partial pressure, okay, which says that if there are n components present in a container, okay, the pressure exerted by each of the component will always be proportional to its amount or will be proportional to its mole fraction. Okay. The one which is present in more amount or which is present in greater amount will exert more pressure. Okay. So, the partial pressure was always equal to the total pressure into mole fraction. Okay. So, we can get the value of YA and YB. Okay. So, just write it down. This is a very important equation. Okay. So, just let us just look at this expression. Okay. So, we have written YA equals to P naught A XA upon P total. Okay. From this I can say that YA upon P naught A would be equal to XA upon P total. Okay. Just I am rearranging this equation. Similarly, YB was equal to partial pressure of B, which is P naught B into XB upon P total. Okay, so we will just take P naught B in the denominator. So, we will get this as upon P naught B equals to XB upon P total. Okay. So, if we add 1 and 2, so we will say that YA plus YB would be equal to XA upon P total plus XB upon P total. Okay. So, if we take P total common, YA upon P naught A plus YB upon P naught B will be equal to XA upon P total plus XB upon P total. So, if we write, if we take the P total common over there, so we will get this as 1 by P total into XA plus XB. Now we know that XA is the mole fraction of A in liquid phase, XB is the mole fraction of B in the liquid phase. Sum of the mole fraction in the liquid phase would be 1. So XA plus XB is 1. So I will get an expression which is YA upon P naught A plus YB upon P naught B would be equal to 1 by P total. Okay, so this is a very important expression. Hope this is clear to everyone. So I can just substitute YB as 1 minus YA. So I can write this as YA upon P naught A plus 1 minus YA upon P naught B equals to 1 by P total. Okay, so I can write this as, if I take YA common, so this will be 1 by P naught A minus 1 by P naught B plus 1 by P naught B equals to 1 by PT. Okay, so this is total pressure over the solution. Okay, so this is basically the expression of total vapor pressure over the solution expressed in terms of mole fraction of vapor phase. Okay. So if you look at this expression, this was the total pressure, okay, over the solution expressed in terms of mole fraction in liquid phase. Okay. So this would be the expression for the total pressure in terms of mole fraction of vapors. So you can clearly see that the dependence on YA and PT, okay, everything over here is a constant. So you will see the relationship between YA and PT would be something like a inversely proportional. So if I want to plot both liquid as well as vapor curve on the pressure versus mole fraction graph, so the graph will come something like this. Okay, so we are not going into detail how exactly this graph is derived. So this is a basic expression that will give us that if we want to plot the vapor, because we knew that this line, the line which is in blue, was representing the total vapor pressure. Okay, hope you remember this. We plotted the Raoult's law, okay, for the two component. So suppose the one component was something like this, the other component was something like this. Okay, so the total is represented by this line. We had done in this thing in the previous lecture. So this is basically representing our total pressure. Okay, so this is in terms of liquid composition. Okay, so if you look at the total pressure in terms of vapor composition, then the graph would come something like this. Okay, hope this is clear to everyone. So just I am using this expression, I am plotting both liquid and vapor together. Okay, so just write it down. I will explain the curve again. Just write it down. This is a very important expression. So this expression gives us the dependence of total pressure on vapor phase, okay, the composition of vapor phase. So just don't get confused. Basically the x-axis is the total composition. We are plotting, initially what we were doing, initially we were plotting just with respect to liquids, we are plotting XA and XB, right, but now this composition axis has everything. It has vapor as well as liquid. Okay, so just write it down quickly. Okay, now if we want to plot both liquid and vapor, both on the same graph. Okay, so we were basically plotting, this was the pressure, okay, y-axis was pressure, and this was the, I will call this now as composition. Okay, basically it is a mole fraction only. So let us assume that XA was 0 over here. Okay, so XA is 1 over here. Now because XA is 1 over here, so XB would be 0. okay, and XB would be 1 over here, okay. So when we are plotting for a single component, okay, so we are saying that suppose the value of P naught A is greater than P naught B, okay. So we know that at XA equal to 1, this would be the vapor pressure of pure A, so that would be P naught A, okay, and suppose this is your P naught B, okay. You can also take this as XA naught, and you can take P naught A, and this you can take as P naught B. It just matters whichever you are plotting, okay. So this is just nothing related to a concept. So if P naught A is greater, because XA is 1, so P naught A would be at a higher level, and because XB over here is 1 and XB over here is 0, okay. So I will say that P naught B is lesser, okay. So if you join them, so this was the Raoult's line, okay. We had just sketched this graph in the previous lecture. Now this was only in terms of mole fraction of components in the liquid phase. Now if you want to plot with respect to vapor phase, so now I understood that this line would represent the vapor phase, okay. So this is actually a very important concept now. So we know that at higher pressure, when the pressure is high, so when you impart high pressure to the molecule will come closer. So when they come closer, they will basically have interaction and they can change into liquid. So we say that at very high pressure, we will have liquid phase, okay, and at very low pressure, when the pressure is low, the molecule will be away from each other and their force of interaction would be negligible, and we will say that they will exist as gas, or we will say that there is a vapor. So basically in this graph we are showing that at very high pressure liquid state exists, at very low pressure vapor state exists, okay. So this line, okay, represents the boundary for the liquid, okay. So basically this will be called as liquidus, okay, liquidus curve, and this curved line is representing a demarcation for vapors. So this will be called as vaporous line, okay, and the region between them will represent the equilibrium between liquid and the vapor phase, okay. So the region between them would represent the equilibrium between liquid and the vapor phase, okay. So in this graph we are showing both the phases, we are showing liquid as well as the vapor phase, okay. But in the initial plot of Raoult's law we are just showing the total pressure in terms of mole fraction of liquid. Now basically I have mentioned this as composition. So this composition has certain value of XA, XB, YA and YB, okay. So I hope this graph is clear to you. Now suppose we consider another case. In this case we have assumed that P naught A is greater than P naught B, okay. When P naught A is greater, it means that it is forming more vapor at a given temperature than B. So it means that A is more volatile, okay. The substance which is more volatile will have more vapor at a given temperature and they will exert more vapor pressure. So we have plotted this for P naught A greater than P naught B, that is A is more volatile than B. Now suppose we want to plot this graph, okay, in terms of same the composition of both liquid and vapor phase taken together, okay. Now suppose that we say that P naught B is greater than P naught A, it means that B is having more vapor pressure, it means that B is more volatile, okay. So we knew that XA was 0 over here, so XB would be 1 over here, XB was 1 over here, sorry, XA was 1 over here and XB would be 0 over here. So when XB is 1, it means that we are having pure B, so let this pressure be P naught B, okay. When XA is 1, we will say that we are having pure A, okay. So the pressure related to it would be P naught A, so let this be P naught A, okay. If you join them, this would represent the total pressure in terms of composition of A and B in liquid phase. Now if we want to, I hope this is looking like a straight line, if not then I will just erase this. Okay, this is basically a straight line. Okay. So suppose this was your okay, so suppose this was your P naught B, P naught A. Okay. So if you want to draw the vapor line as well, so the vapor graph would look something like this. Okay. So at higher pressure we know that liquid phase is stable. So we know that at higher pressure liquid would be present, at lower pressure vapor would be present. So this line basically represents the liquid or the liquidus curve. This curved line represents the vapor curve, and the region between them represents the liquid and vapor in equilibrium. Okay, I will just explain this graph when I discuss a concept of distillation. For the time being, you just draw this graph. These graphs are also very important. Okay, so basically what we have done, we have sketched a graph of pressure with total composition. Total composition means this composition has, okay, suppose I am at this point. So at this point we will have vapor. So this will have the composition of vapor, YA and YB. Okay. So suppose we are at this point. So this will have only liquid. So the composition corresponding to it would be XA and XB. Okay. What would happen when we will be inside the graph? I am just going to discuss it. Okay. So we say that whenever we are plotting pressure versus composition graph, the graph would look something like this. Okay. Just draw it. Hope this is clear to you. So what I have done till now, I have just told you that whenever we are having mixture of liquid and both the liquids are volatile, so both the liquids will form some amount of vapor, okay, and that vapor individually would exert some vapor pressure on the surface of the liquid. Okay. The total pressure exerted over the solution would be the sum of their partial pressures of the, okay, sum of the partial vapor pressure of the liquid. Okay, so that PT was equal to PA into PA plus PB. Now PA we know from Raoult's law is P naught A into XA, PB is equal to P naught B into XB. So that was total pressure in terms of composition of A and B in the liquid phase. Now if we want to calculate the composition of vapor phase, we said that let YA be the mole fraction of A in vapor phase and YB be the mole fraction of B in the vapor phase. So YA would be the partial pressure of that component upon the total pressure exerted. Okay, so that was PA upon PT. PA is P naught A into XA, PT is P naught A XA plus P naught B XB. Similarly, YB would be the partial pressure of B upon the total pressure. So that would be P naught B into XB upon P naught A XA plus P naught B XB. Okay, then we derived a important relationship between the total pressure and the mole fraction of A and B in vapor phase. Okay, so just remember these are two very important formula, this one and like this one. Okay, so from there we came to know that the dependence on the total pressure and vapor phase would be something equivalent to inversely proportional graph. So if we plot both of them together in a single graph, so we will get this as the curve. The blue one represents the liquid, the red one represents vapor. So that what we have sketched over here, assuming that A was more volatile in the first case and in the second case B was more volatile. These graphs are of immense importance. If you understand this graph, the concept of dew point, the concept of bubble point would be very easy to explain. Okay. So let us first start with some of the question. Okay. So just read this question. Now this question says that we are mixing 1 mole of a benzene whose vapor pressure is given to us as 120 mm of Hg is mixed with 2 moles of toluene whose vapor pressure is given to us as 60 mm of Hg. Find the mole fraction of vapor formed and the total pressure developed over the solution. So this is basically a direct application of the concept which we have done. So we know that the mole fraction of A or the mole fraction of benzene, okay, in liquid phase would be moles of benzene is 1, total moles is 3. Okay. So the mole fraction of toluene in the solution would be 2/3. Okay. Small x will always denote mole fraction in liquid phase and y would always be representing mole fraction in vapor phase. Okay. So these are the mole fraction that are given to us. So we also know that P naught of benzene is 120 mm of Hg and say that of toluene as given to us is 60 mm of Hg. Okay. So the total pressure developed over the solution would be the sum of their partial vapor pressure. Okay, partial vapor pressure is the pressure exerted by the individual component in the total pressure. Okay. So Pt in this I can say using Raoult's law, this would be P naught benzene into x of benzene. So P naught benzene is 120, x of benzene is 1 by 3, P toluene is P naught toluene into its mole fraction, so which is 60 into 2 by 3. So if we just do the calculation, so this is basically 40 and this would be again 40, so we will get 80 mm. Okay, 80 mm of Hg is the total pressure developed. Okay, so this is basically 3 into 40, this is 3 into 20, so 80 is the total pressure exerted. Now if we want to calculate the mole fraction of vapor formed, okay, so the mole fraction of benzene, I have already told you that anything in vapor would be represented by the mole fraction which is written as Y, okay, liquid is written as X. So Y benzene would be the pressure that is exerted by benzene in the total pressure divided by the total pressure. So the mole fraction of benzene, I can say this is P naught benzene into, okay, P naught benzene into mole fraction of benzene in the liquid phase. So this would be 120 into 1 by 3 and total we have already calculated at 80. So this would come out to be 0.5. Okay, similarly we can calculate for Y toluene, mole fraction of toluene in vapor phase. This would be pressure of toluene upon total pressure. So the pressure exerted by toluene would be 2 by 3 into 60, that is 40, 40 by 80 is again 0.5. Also we know that the sum of their mole fraction would be 1. So this is the answer. Okay. So this is a direct application of the formula that can be asked in JEE Mains, but generally the question becomes trickier. So we will see other aspects of the question as well. Okay. I hope you have written this question and taken this snapshot quickly. Okay. So just read this question. Now this question says that what is the composition of the vapor which is in equilibrium at 30 degrees Celsius with benzene toluene solution with a mole fraction of benzene as 0.4. Okay, where pressure of pure benzene is 100 and that of toluene is 80. Okay, so this is again a very simple question. So the mole fraction of benzene is given to us in liquid phase is suppose 0.4. So that of toluene would be 0.6. Okay, so we have been given the pressure of pure benzene as 100 and pressure of toluene as 80 mm of Hg. Okay, so we can calculate the total pressure. The total pressure would be the sum of the partial pressure of benzene as well as toluene. Okay, so this would be 0.4 into P naught benzene into its mole fraction plus P naught toluene into its mole fraction. So this would be 40 plus 48. So that is 88. Okay. We have to find the composition of vapor. So the mole fraction of benzene in vapor phase would be partial pressure of benzene upon total pressure. Okay, total pressure we know is 88. Partial pressure of benzene would be 0.4 into 100. Okay, divided by 88. So this is basically 40 upon 88. And that of toluene would become 48 by 88. Okay, so you can calculate this. So again, this is again a direct application of the concept. Okay, so if you can see, basic solving is a very important concept of understanding the formulas. If you do more of a basic solving, then you will easily remember the formulas and the concepts involved behind those formulas. Okay, and that actually helps in higher level problem solving. Okay, so just read this question now. Now this says that liquids X and Y form an ideal solution. The vapor pressure of X and Y are given as 300 and 100 mm Hg. Suppose that a solution composed of 1 mole of X and 1 mole of Y at 100 degrees Celsius is collected, okay, and condensed. So the first part of the question is we were taking 1 mole of, okay, so it's something like this. So we are having in a container 1 mole of so we are having 1 mole of A and 1 mole of B. Okay, so some vapor would be formed over here. Okay, some vapor would be formed over here of A and B. Okay, now this is collected, the entire vapor is collected and condensed. So initially the vapor formed, all the vapor formed were collected and condensed. Okay, hope this is clear to you. So the vapor formed over here were condensed. Okay, so when we condensed it, so we would have got it as liquid now. Okay, I hope this is clear. So the vapor formed over here were condensed and we got the liquid, and that liquid or the condensate, okay, so we basically the whatever liquid we are getting, we are calling it as condensate. The condensate was again heated and the vapor formed. So again vapor would be formed over here. Okay, so this condensate is heated at 100 degrees Celsius and the vapor is again condensed to form liquid A. Okay, so basically we are again condensing this vapor into a liquid. Okay, so the question is saying what is the mole fraction of X in A. Okay, so basically we have to get this. So now let us build the basic concept that we have done till now. So let us look at the first jar. We know that it had 1 mole of A and 1 mole of B. So the mole fraction of A was half and the mole fraction of B was also half. Okay, so the total pressure developed over this solution would be, okay, basically it is X and Y. So this is 1 mole of X and this is 1 mole of Y. So the mole fraction of X in this case would be half and the mole fraction of Y in this case would be half. So the total pressure developed over the solution would be half into 300 plus half into 100. Okay, so this is 200. Okay, 200 mm. So the vapor pressure of X in the vapor phase, okay, the mole fraction of X in the vapor phase would be the partial pressure of X upon total pressure. So the partial pressure is half into 300, that is 150 upon 200. Okay, so this is basically 3 by 4. Similarly, the mole fraction of Y in vapor phase would come out to be 1 by 4. Okay, so this is the calculation in the first container. Now we are condensing the entire vapor into liquid. Okay, so when we got liquid over here, so we'll say that the mole fraction of X in the liquid phase would be 3 by 4 and that of Y would be 1 by 4. Hope this is clear to everyone. Okay, because we are condensing all the vapor into the liquid, so whatever composition of vapor is there, it would convert into the composition of liquid. So this is the mole fraction of X and Y in the liquid phase in the container B. So the total pressure over this solution would be the mole fraction of X in liquid state into its partial pressure, which is 300, plus the mole fraction of Y in liquid phase into its vapor pressure. Okay, so when you do this, you will get total pressure as, this is 900 plus 100,000, so this we will get as 250 mm. Okay, so the total pressure exerted is 250 mm. Okay, I hope you have understood this now. Just look at the step that we are doing. So the mole fraction of vapor X in this container would be partial pressure of A upon total pressure. Okay, so this is basically 225 upon 250. Okay, so mole fraction of Y in vapor phase. Okay, mole fraction of Y in vapor phase would be the pressure exerted by, okay, the Y component divided by total pressure. So this would come out to be 25 by 250. So this is basically 1 by 10 and this is basically 9 by 10. Okay, so we can say that in this liquid, now all the vapor are again condensed over here. So in this liquid, the mole fraction of X in liquid phase is 0.9 and the mole fraction of liquid Y is 0.1. Okay, so that is what is asked over here. Now the last question in this could be find the ratio of vapor over here. Find the ratio of vapor of X and Y. Okay, so again you have to do the same thing. You have to calculate the total pressure over here. So the total pressure over the solution would be 0.9 into 300 plus 0.1 into 100. So that would give us the total pressure. Okay, and we can find the mole fraction of vapor of X as well as Y using the same equation. Okay, and we'll get the value of mole fraction of Y in vapor phase and X in vapor phase, and we'll take the ratio. Okay, so if you want to calculate that, so we'll say that the total pressure exerted over here is suppose PT double dash. So this is PT double dash. So this would be the mole fraction of X into its vapor pressure plus mole fraction of Y into its vapor pressure. So this is 280 mm of Hg. Okay, so the mole fraction of X in vapor phase would be 0.9 into 300 divided by 280, so that would be 27 upon 28, and the mole fraction of Y in the vapor phase would be 1 upon 28. Okay, so what we can say? We can say that the ratio of Yx upon Yy is 27. Okay, so this could be another question. Now this was a question in JEE Advanced. I think it was there in 2018. Similar lines. Okay, similar lines question. So just you have to understand the basic concept. So one thing which you will see over here, okay, if you look at X and Y liquid, X has higher vapor pressure than Y. X has a vapor pressure of 300 and Y had a vapor pressure of 100. Okay, so X was more volatile than Y. So initially the vapor formed would be more of X, as you can see in the data also. The mole fraction of X in the vapor phase was more than that of Y. So over here, okay, in the liquid we'll have more composition of X and less composition of Y. Now when this is forming vapor, we were having the mole fraction of vapor as 9 by 10 and 1 by 10. Okay, so the mole fraction of vapor Y has increased further. So when you condense this, okay, so we get the mole fraction of X in liquid phase as 0.9 and Y as 0.1. If you look at the vapor composition over here, so the mole fraction of X in vapor phase is 27 by 8 and that of Y is 1 by 28. So you can see if you keep on doing this process continuously, so we will see that ultimately we will be left with a pure Y and X will remain in the liquid solution. Okay, so if you keep on doing this process n number of times, you can clearly see that we are increasing the component which is having more vapor pressure on is more volatile. So more volatile compound or the more volatile liquid will form more vapor. Okay, so if you keep on doing this, so it will keep on forming more vapor until both liquid X and Y are separated. Okay, so this is also the way you can separate these two liquids. Okay, I hope this question is clear to you. So this basically involves a basic application of the formula which we have done, and this is how JEE will ask you. They will never ask you to use the direct formula, they will obviously try to use it in some application. So you have to understand what exactly is being done. Okay, if you look at the composition of vapor over here and the composition of vapor over here, okay, the ratio of the composition of vapor was 3:1. Now it is here 27:1. That means the vapor is getting richer in more volatile component. So if you keep on doing this process, ultimately we will get the vapor of only one of the liquid and the other liquid would separate out. Okay. So I hope this is clear to everyone. Okay. So let's enter into the main concept that I wanted to discuss over here, that is isothermal distillation. Okay. Now this is not there in your syllabus, not mentioned in your syllabus, but this has very important concepts that will actually make you help in problem solving, and these like difficult problems would become very easy using this concept. Okay, because this concept explains you the detail of everything that is being framed in the question. Okay, so if you have understood this, then the most difficult questions of vapor and the liquid phase you can easily crack it. Okay, so what exactly is distillation? We know that distillation is the separation of two liquids based on their boiling point. So what we are going to do, we have already mixed two solutions, two liquids A and B, and both of them were volatile. Okay, so we are just going to distill it and we are going to understand what would happen at different points. Okay, so let us say we are having a suppose we are having a liquid, okay, at a certain temperature. Okay, so suppose this is our liquid phase. It is contained in a container fitted with a movable piston. Okay, now let us try to understand this through our graph concept. So we have already plotted this graph, that when we are plotting the pressure versus the composition, the pressure versus the mole fraction. Okay, okay, so we have already plotted this graph. Say this was the graph. Okay, I hope you understood how we have drawn this graph. I have already explained in the previous slide. Okay, so let me draw it properly. It's not a whiteboard. Okay, so this was the graph. So we said that at higher pressure liquid phase is there, and at lower pressure vapors are there. So this line would represent the liquid line and this line would represent the vapor line, and the region between them is liquid and vapor. Okay, so just listen to this very important concept. So I hope you are listening to it properly. So suppose we are, say, at this composition. Okay, so we are at this point. So this is basically your liquid point. Okay, so this will have some composition we can find directly by dropping a perpendicular on the composition graph. So this composition is having both liquid as well as vapor component. Okay, so now if we want to convert this liquid into vapor, if from this state we want to go to this state, okay, so what we have to do? Isothermally we are going to reduce the pressure. Okay, we are reducing the pressure. So once we start reducing the pressure, okay, once we start reducing the pressure, so we'll come at this point. Okay, let this point be called as P. Okay, now what would happen at this point P? Okay, so we are going to talk about point P. Now at point P we'll say that the first trace of vapor is formed. Okay, at point P the first trace of vapor would be formed. A was like the composition corresponding to A was that of liquid, so A is basically liquid, it is in the liquid zone. So what we are doing isothermally, we are just decreasing the pressure. So when we are decreasing the pressure, that means we are lifting the piston. Okay, so we'll say that at some point of time we'll get some amount of vapor. Okay, so this point B is called as the point where the first trace of vapor is formed. Okay, so the first trace of vapor could be seen through the bubble that is forming in the liquid. As you can see in your home as well, when you boil the water, okay, you can see that there is a bubbling happening at the water, indicating that water has boiled, boiling point has been reached and the liquid is converting into vapor phase. Okay, so when the first trace of vapor is formed, you can see a bubble in the liquid. So this point is also called as the bubble point. Okay, so this point is also called as the bubble point. So we will refer this point as, okay, so this point is called as the bubble point. Hope this is clear to you. Okay, so at point first trace of vapor is formed, this is called as the bubble point. Okay, now the first thing that should come in our mind, at what pressure does this first trace of vapor has formed? So we can clearly see this would be the pressure at which the first trace of vapor is formed. Okay, so we can also calculate it using the Raoult's law. So we'll say that pressure at which first trace of vapors are formed would be, okay, P naught A XA plus P naught B into XP. Okay, where XA would be the mole fraction of A in liquid phase and XB would be the mole fraction of B in liquid phase. Okay, so I hope this expression is clear. So this would be the pressure at this point, okay, where the first trace of vapor is formed, or we also call that point as the bubble point. Okay, now the second thing that should come in our mind is what is the composition of the vapor. Okay, so what is the composition of the vapor? So the composition of vapor at the bubble point, okay, YA would be the pressure exerted by the vapor A upon the total pressure. So this would be PA upon PT, that would be P naught A XA upon the PT that we have calculated over here. Okay, so we are saying this is PT. Okay, similarly we can find the composition of vapor B, okay, that would be PB upon PT, that would be P naught B upon P naught B into XB upon PT. So this would be the composition of the vapor formed at the bubble point. Okay, so this is just the same expression that we have done till now. Okay, hope this is clear to everyone. So we are starting with the point A and isothermally we are just reducing the pressure. We reached a point B where we can see that the first trace of vapor is formed. So that can be seen through a bubbling that has happened in the solution. So we will say that we have reached a bubble point. Now as we keep on decreasing the, okay, now as we keep on decreasing the pressure, okay, we will be entering into the liquid vapor equilibrium zone and then finally we will be going to the vapor phase. So let us see what is happening at P point. Okay, so basically we have called this as, say this is our B point, okay, and this is P. Okay, so okay, let us consider this was point B and not P. Okay, so at this point the question can be what is the composition of vapor. So I will say that the composition of vapor can be seen by just joining it with the vapor phase line. Okay, so because this line represents the vapor, so the composition of the vapor would be this. Okay, so which we are finding over here. So the composition of the vapor would be by just dropping a perpendicular on the vaporous graph. Okay. Now if we keep on decreasing the, okay, if we keep on decreasing the pressure, suppose we reached a point C over here. Okay. Now this C will have both liquid and vapor, okay, because we have entered into a liquid vapor equilibrium zone. So the composition of the vapor could be found out by just dropping a perpendicular on the vaporous curve, and if we want to find the composition of the liquid, okay, we will drop a perpendicular on the liquid graph. Okay. So if you go over here, so we'll get the total composition of the liquid. Okay. If you go over here, we'll get the total composition of the vapor. Okay. Similarly, we are reducing the pressure and we reached a point C. Suppose this is the point C. Okay. So what would happen at point C? We'll say that at point C, almost all the liquid has converted into vapor. Okay. Because at point C, after point C only there is vapor. So we'll say that at point C, last trace of liquid remains. So at point C, last trace of liquid remains. Okay. So this is called as the dew point. Okay. So this point is known as dew point. Okay. So we'll call this as dew point. So at point C, we'll say that last trace of liquid has remained. It means that all the liquid has converted into vapor phase. Okay, last trace of liquid remains. That means all the vapor has almost converted into vapor. Almost, not complete. We'll say that almost all the liquid have converted into vapor phase. So the composition of vapor over here would be approximately equal to XA, because all the liquid of composition XA has vaporized into. Okay. Similarly, we will say that YB is equal to XB, because all the liquid of composition XB has changed into vapor. So we will get the value of YA and YB. Now we want to find the pressure at this point. Okay, so we want to find the pressure at this point. So from the graph we can easily make out. Now if we want to calculate, so I am just going to use the formula. I have already derived that formula, that's why I told you that formula is very important. So that formula was basically calculating the total pressure in terms of mole fraction of A and B in vapor phase. So that would be YA upon P naught A plus YB upon P naught B equals to 1 by PT. Okay, so from here we will calculate the total pressure. So suppose this is your PT dash. Okay, so this would be PT dash. This was your PT which you have calculated. Okay, so this is one important expression. Okay, so from here you can calculate the total pressure. Okay, so a question like this can come in your JEE. Like they will ask that suppose we are having a liquid of composition A, at what, okay, pressure range there would be an equilibrium between liquid and vapor. So we know that between PT and PT dash pressure there would be an equilibrium between liquid and vapor phase. Okay. Now let us find out the last thing, that is, okay, so this was basically the pressure at dew point. Okay, so we calculated the pressure at dew point by this. Okay, now what would be the composition of the liquid at C or at dew point? Okay, so we will say that at C or the dew point entire liquid has changed into the vapor. Like not entirely, almost, like we will say that almost all the liquid has changed into vapor, but some amount of liquid will be left. That would be very small, but if we want to find the composition of that liquid, how we will calculate? So we know the total pressure at that point, so we will directly say that PT dash, use the Raoult's law equation, that would be equal to P naught A into XA. Now this XA would be the, right, this XA would be the mole fraction of A in liquid phase at this point C. So don't confuse this and this. So both of them are different. So PT dash would be equal to P naught A XA plus P naught B into XP. Now this XA and XP would be the mole fraction of A and B in liquid phase at dew point. Okay. So now when we further lower the pressure, we will come to the point B. Okay. So this is a very important conclusion. So direct questions comes on these 4 parameters. Okay. So just write it down. I will quickly explain you once. We will solve a question also on this. So we are saying that we are going to isothermally distilled, okay, a mixture of liquid A and B. Okay. So we are saying that this was the graph. We have already seen how this graph has been sketched now. So we were sitting at a point A. Now that point would represent only liquid phase. We can calculate the composition but just by dropping the perpendicular on the x-axis. Okay. So we will be getting the total mole fraction of A. So we will get the individual mole fraction of A and B. Okay. Now what we are doing at a constant temperature, we are just lowering the pressure. So we are just, okay, taking this piston outside. So the pressure would start decreasing. So the pressure start decreasing. Suddenly a point B came. At this point the first trace of vapor appeared. Now the first trace of vapor, if it is appearing, you can clearly see a bubbling in the solution. So that vapors are formed. So that is called as the bubble point. So at the bubble point, the total pressure would be P0 A XA plus P0 B XB, where XA and XB are the mole fraction of A and B in the liquid phase. The composition of vapor at bubble point would be YA, that is PA upon PT, YB PB upon PT. Okay. Now on further decreasing the pressure, suppose you land up at a random point D. Okay. So this, we know that there would be a region of equilibrium between liquid and vapor, because the area between the two lines represent the liquid vapor equilibrium. So if you want to get the composition of vapor at D point, so you can just drop a perpendicular to the vapor graph, you will get the value of the composition of vapor. When you drop the perpendicular to the liquid graph, you will get the composition of the liquid. Okay. So there is a concept of lever rule over here. This is basically called as the tie line. The line that is perpendicular to the mole fraction axis is called as tie line, TIE. It is called as tie line, and there is a lever rule given over here, which we will discuss when we discuss Olympiad level problems. Okay. So on further decreasing the pressure, we reach a point C. At this point, we will say that almost all the liquid has converted into vapor. So we will call this as a dew point. So at dew point, the composition of, okay, the composition of the vapor would be equal to that of liquid only, because entire liquid has almost changed into the vapor. So YA over here would be equal to XA, YB would be equal to XB. Okay. So from that we can calculate the total pressure at dew point. So we are writing the pressure at dew point as PT dash. Okay. Now we can also calculate the composition of the liquid at this point, because we know that total pressure is always P0 XA plus P0 A into XA plus P0 B into XB, where XA and XB are the composition of A and B at point C. Now on further decreasing the pressure, we will get only vapor phase. Okay. So I hope this is clear to everyone. This is actually one of the most important concepts for JEE Advanced. Okay. Questions can definitely come on this, because this has a lot of practical importance, as well as this is deeply conceptually enriching concept. Okay. So I hope you have got this completely. Okay. So you have written it completely, and you have understood the concept. Okay. If you have understood the concept, most of the questions on liquid and vapor compositions would be solved. Okay. So let us look at a question. Okay. So this is the question, just try to solve it. So this says that we are taking a mixture of benzene and toluene. This is composed of 1 mole of benzene and 1 mole of toluene. If the pressure over the mixture is reduced, at what pressure does the first vapor formed? Okay. So you can see this is the same thing which we have discussed now. Okay. So we are just reducing the pressure. So we want to get the pressure at the bubble point. Okay. So the first question is the wave pressure of, if the pressure over the mixture is reduced, at what pressure at the first trace of vapor be formed. That means you are talking about bubble point. So at bubble point we know the total pressure is the partial vapor pressure of both the components. Okay. So this would be according to Raoult's law P naught benzene into mole fraction of benzene plus P naught toluene into mole fraction of toluene. Okay, so this would be PT. So we'll say that PT will be equal to 100 is the, okay, if we have not been given the pressure of benzene is 100 and toluene is 30. Okay, so this is 100 into half plus 30 into half. So this would be 65 mm. Okay, now it is saying the composition of the first trace of vapor. Again, we want to find the composition at the dew point, composition at the bubble point. So we'll say that YA will be equal to PA is 50 upon 65, total pressure is 65. So we can write this as 10 by 13. So YB would be, YA plus YB is 1. So I can write this as 3 by 13. So we'll get the mole fraction of A and B, or benzene. Suppose A was your benzene and B was your toluene. So that is 10 by 13 and 1 by 3 by 13. Okay. Similar, the same question continues. Okay. The D part is, what is the composition of the last trace of liquid? Okay. So what is the composition of the last trace of liquid? So when the last trace of liquid is there, it means that, okay, it means that almost all the liquid have converted into vapor. It means that we have reached dew point. So we'll say that the composition of vapor of benzene in the vapor phase would be equal to the mole fraction of benzene in the liquid phase, because all the liquid phase has converted into vapor phase, and similarly that of toluene would be half. Okay. So we know Y benzene upon P naught benzene plus Y toluene upon P naught toluene. So we are just going to use the equation that relates total pressure and the vapor pressure and the mole fraction of vapors. So we'll just use the value. This is half, benzene is 100, this is also half, and this is 30. Okay. So we'll get the total pressure over here. So I can write the total pressure as, this would be 4 into 100 into 30 divided by, if I just add them, so this would be 200 plus 60, so this would be 260. So this would be the total pressure at the dew point when all the liquid have started to disappear. Okay, and then you have to find the composition of the last trace of the liquid. So the composition of the last trace of liquid, I can say that, okay, the composition of the last trace of liquid would be, I have got the total pressure as 400 into 30 divided by 260. Okay, so we'll directly use the Raoult's law formula. So that this would be P naught into mole fraction of benzene plus P naught of toluene into mole fraction of toluene. So this is 400 into 30 upon 260. Okay, so the benzene vapor pressure is 100 XB plus toluene is 30, and we can write XT as 1 minus mole fraction of benzene. So we can calculate the mole fraction of benzene from here, and we can calculate it for toluene as well. So you can see this was a direct question on that graph, and many a times in many of the content, in many of the booklets, in many of the coaching materials, in many of the different test questions, you will find such kind of question. So if you are clear with this graph, okay, if you are clear with this graph and different points, so the question becomes very easy, and this is considered as one of the tough questions of this portion. Okay, so the question was basically we are having 1 mole of benzene and 1 mole of toluene. We reduce the pressure. At what pressure does the first vapor formed? Okay, and what is the composition of that first vapor? At what pressure does the last trace of liquid disappear and the composition of the last trace of the liquid. Okay, so just write it down quickly. The last part is what will be the pressure, the composition of the liquid and the composition of the vapor when 1 mole of the mixture is vaporized. Okay. So we'll just solve this now. Hope this is clear to everyone. So this is saying that when we have half of the mixture is vaporized, what would be the pressure? If we calculate the pressure, we can find out the composition using Raoult's law. Okay. So now we knew that we had 1 mole of, okay, so we had 1 mole of benzene. We are solving the last part of this question. So we are having 1 mole of benzene and 1 mole of toluene. Okay. So this is saying that what will be the pressure, the composition of the liquid and the composition of the vapor when 1 mole of the mixture is vaporized. So total mole of the liquid was 2. We have vaporized half of it, so that the amount of liquid left is 1 mole. That is what question is saying. You can clearly read that when 1 mole of the mixture is vaporized, 1 mole would be left. Okay. So let us assume that let the moles of vapor of benzene be X, okay, and that of say toluene be Y. Okay. So we have assumed that X is the moles of vapor that has come over here and Y is the moles of toluene that has come in the vapor phase. So we know that because half of the liquid mixture has vaporized, that means 1 mole of this mixture has vaporized. So the total moles of vapor formed would be 1. So we know that the value of X plus Y over here is 1. Okay. So the moles of benzene in liquid phase would be 1 minus X, okay, because X mole of benzene has vaporized. Similarly, moles of toluene in liquid phase is 1 minus Y. I hope this is clear to you. Okay. So the mole fraction of benzene in vapor phase would be, okay, so Y already represents vapor, but I am writing that so that you don't get confused. This will be moles of benzene upon total moles. Okay, so this would be X only because X plus Y is 1, and the moles of toluene formed at the mole fraction of toluene in the vapor phase would be moles of toluene upon total moles, so that would be again Y. Okay. I hope this is clear to everyone and you are able to understand. Okay. So we have to find the total pressure when half of the mixture has vaporized. Okay. So I can write the expression of total pressure. Now we know that the total pressure in terms of liquid, I can write this as P naught of benzene into 1 minus X plus P naught of toluene into 1 minus Y. Okay. Also I can say that, okay, PT is equal to P naught B plus P naught T, okay, minus X plus P naught B plus P naught T. Oh, sorry. This is in terms of X and Y. So this would be P naught B plus P naught T minus, okay, X into P naught B minus Y into P naught T. Okay. Now somehow we need to cancel out X and Y so that we will able to get the total pressure, because none of the data has been given to us, because we need to find this total pressure. So one thing I can say that, okay, YB is equal to the partial pressure of B, that is benzene, upon the total pressure. Okay, so we know that YB is equal to X. Okay, I will say that the partial pressure of benzene, okay, is P naught B into, we know that the mole fraction of liquid in liquid phase is 1 minus X upon total pressure. Okay, so the total pressure I know is P naught B 1 minus X plus P naught T 1 minus Y. Okay. Okay, I hope you have understood this. Now we'll just take this quantity to the right hand side, okay, and just we'll multiply. Now we know that the value of X plus Y is also 1. Okay, so the value of X plus Y is also 1, so we can use the value of Y as 1 minus X. Okay, so you can put the value of Y as 1 minus X and everything would come in terms of X. So we'll get X in terms of P naught B and P naught T. P naught B is the partial pressure of benzene and P naught T is the partial pressure of toluene. Okay, so just you can carry out the necessary calculation. So just look at the problem. Okay, this is again a very good high level problem. Okay. There's a problem in this. Okay, just wait. I got this over here. So we haven't calculated the mole fraction of benzene and toluene in liquid. Okay, so that is why we are not getting a good expression. We are getting a very off equation over here. So because like this is the error which every one of us make, not finding out some datas. So this was not the mole fraction, this was the mole, because right, this was not the mole fraction. Mole fraction would be 1 mole of benzene and 1 mole of toluene was there. Okay, so when we have evaporated, okay, now when we have evaporated the half of the mixture, so the total moles left would be, okay, 1 only. So this would be the expression only. Okay, so the mole fraction of benzene and toluene in the liquid phase would be 1 minus X and 1 minus Y. So again we have to use the same equation only. So you have to put the value of PB as P naught B into XB. Okay, the total pressure we know is, like, you can calculate the total pressure. Okay, so we'll say that YB is equal to X. Okay, YB is equal to X and PB is equal to P naught B into 1 minus X upon PT. So I can write PT as P naught B 1 by X minus 1. Okay. Okay. So if you put the value of PT as P naught benzene into X of benzene plus P naught B of toluene into X of toluene, you will get the value of PT, and then you can use the equation and you can find out. So in that case you can see that PT comes out to be equal to root of P naught benzene into P naught toluene. So you can just try this. I will discuss it in the next lecture if you are not able to get it. So this is the basic idea. 1 mole of mixture has evaporated. That means if X moles of benzene was formed as vapor, Y moles of benzene was formed as vapor. So the value of X plus Y would be 1. So the vapor of the mole fraction of benzene in the vapor would be X. The mole fraction of toluene in the vapor phase would be Y. The mole fraction of benzene in the liquid would be 1 minus X, and that of toluene would be 1 minus Y. So basically you have to write the expression for the total pressure, okay, and just you have to use the equation and cancel out X, okay, and you will get the value of in terms of P naught B and P naught T. Okay, so just do the calculations. In case you are not able to do it, I will show you the solution step in the next class because we have already exhausted our time. Okay. So this is again a very beautiful question. In case of any doubt, I will refer this question in the next lecture. So I hope you have understood this graph, okay, this entire mechanism of distillation, and I hope you have understood these type of questions as well and how we are sketching these graphs, okay, and what was the composition of vapor. Okay. So the last question which we are trying to solve, which we couldn't due to lack of time, I will get back to this question in the next class. I hope you are able to understand the concept that was demonstrated today. The concepts today were little tricky, were little difficult. The questions are also difficult and tricky in this case. So what I would suggest you, just go to the lecture once, solve the daily practice problem sheet because that has a lot of question on the composition of vapor. So that will help you building the concepts and that will actually help you in cracking such kind of question because this is a very important topic for IIT-JEE. This can definitely come in the JEE advanced paper and has even come in many of the previous papers as well. Okay, so this is it for today. So we'll catch up in the next lecture with some more interesting sessions. Thank you, students.